Which I think you need to as you're climbing, you need to accumulate. You're going to accumulate in some continuous way, drift westward. But that's not what I'm going to do. I'm going to say we climb quickly,
Okay.
and then we sit at a particular altitude.
Mm-hmm.
And if we sit at that altitude, how much drift do we have over time at that altitude? Which is not quite what's going to happen, but
You're taking the big picture. You're saying there's a lot of accumulation of horizontal drift as you go, but let's just zoom out and get the end result.
yeah.
Okay.
So so this line here is difference in speed
Mm-hmm.
is r omega final minus r omega initial, and the r omega final is r plus delta r times omega final,
Mm-hmm.
and the r initial, which is the person sitting on the surf. What's going on here?
I'm trying to zoom in, but I lost which button does that.
Oh. I see it, upper right.
Okay.
Okay.
There we
So
go.
yeah. So if we plug in, so for example, I think this will make sense once we get to this table, if this
Okay.
isn't clicking. So if we plug in delta R equals 160,000 meters, which is
Okay.
low Earth orbit, then we get a delta V between the surface of the Earth and low Earth orbit of 11 meters per second. I think I just plugged that in.
But lower Earth orbit.
And
Okay, so now you're ready. Okay. So if I can
yeah.
understand this,
Mm-hmm.
you're looking for the tangential velocity,
Yep.
and you have a known surface of the Earth. This is a parameter
Yep.
that you're going to vary, and
Yep.
you have a known surface of the Earth. You have a known angular speed of when you're on the
Mm-hmm.
surface. So you're going to you're going to vary this number to get final angular
Yep.
velocity. Wait, what's
Yep.
your final angular velocity? How did you solve for this number?
That's what we solved at the top there. It's this thing.
I see. So you plugged this thing into there.
Yeah. And I did not show it plugged in. I guess I could have. Oh, and then maybe I should have, because look at this, the r plus r squared on the bottom, r plus delta r squared on the bottom, one of those cancels, which simplifies the calculation.
I think that's a good idea. Yeah.
Yeah. Okay, and okay, hold on. I think I have a calculation on Desmos that shows me making these calculations. Let's see if I can bring that up here
I
and
got it.
share it with
This
you.
thing?
Oh. Let me see. Did I share one with you?
I don't know if you shared it with me, but I see it on the board.
Okay. That's cool. I see it here.
Go internet.
That's cool. Okay, maybe I reshare. Let's see if I can do this here. Share your saved graph. Copy. Let's try this again.
Oh, okay.
Oh,
I've got some
there it is.
line here.
Yeah, okay. The critical part is the left side of the calculation here. The left side column of
Over here.
calculations. This is where I plugged in the numbers. And yeah. And I think if you see the vertical scroll bar, you can pull that to the right to get more space.
Much better.
Yeah. Okay. So I think, what did I do here? This is, I'm calculating the delta. This is the angular speed final.
Mm-hmm.
Oh, sorry, angular speed final.
Okay.
If you climb a certain distance. And I did it, for several, I see what I'm doing here. If you go to the top calculation, very, very top, I'm going up 1 meter. There's ones in there.
That's here. Here's your
Next one.
delta R.
Yeah. Next one, I'm going up 10 meters.
Mm-hmm. 100,
100
1,000,
meters.
10,000.
10,000. And I think if we keep going, there is...
This is a different line.
Different line. So this is new calculation
1
here.
meter.
Oh, this is I didn't update this. This is now the a different calculation that I did in the past, which I abandoned because it was overly complicated. So I think, okay, so if we go back to, maybe I need to update these calculations then. If we go back to the LaTeX, gosh, because now we're going to have to assume these numbers are right. So the delta V, assuming I plugged in, maybe if we scroll all the way to the bottom of those calculations, maybe I did it at the bottom.
This is it. This is the end of the doc.
Oh, I'm saying on the
Desmos. Oh, yeah.
Yeah, go all the way to the bottom. All the way to the bottom. Yeah, look at that, right there. I think that's it. So I plugged in 160,000, which is low Earth orbit.
Okay.
And it's not square.
I guess you
no,
put
it
in
is squared at the bottom.
40,000 because the expression has this d delta r squared.
All right, and isn't it square? It's
Oh
squared
no,
on the
no,
bottom.
so
there.
you're right. 160,000 then square it.
Yeah.
Okay.
And then I multiplied by the same thing on the top, which keep following. Yeah, that thing. That's kind of redundant, but. And then I subtracted the surface of the Earth velocity.
Okay.
Okay.
Then the end
So
result
this
was minus 11.
0.3669.
Change.
Yeah. And if we go to Miro, not Miro, LaTeX, there it is. 11.3669 meters per second.
Here.
Up a little bit. Yeah, right
Change.
there.
So the difference in velocity in the horizontal velocity, if you go up to low Earth orbit relative to the surface, is you get 11 meters per second. Effectively, it looks like you're traveling 11 meters per second to the west.
To the west, yes, for a person sitting on the surface of the Earth.
Okay.
And then this table is if I'm sitting at low Earth orbit, moving 11 meters per second west for 1 second, I have a movement west, a drift west of 0.011 kilometers. And then I did it for different. Go ahead.
For longer time intervals for that given velocity, you drift further in distance.
That's right. In fact, after an hour sitting at low Earth orbit at 11 meters per second difference, you accumulate 50 kilometers of westward movement.
Oh, boy.
Significant.
So you send a payload, and it really doesn't end up where. I mean, depending on how fast this thing goes up, the ladder, what would we call it? The space elevator. Then you really need to aim. Like if it takes an hour to go up to low Earth orbit, you really need to aim 50 kilometers to the west to get to land at the right spot.
Yeah. So I think the next calculation is if now we got to do a continuous addition or an integration of the drift. So if you go up a tiny bit, you drift a little bit, go up a little bit, drift a little bit, go up a little bit, drift a little bit. I think that's what we have to do.
It.
Yeah. Whereas this is just at a particular elevation. But the drifts are significant, which means if we go back to, I think this means the drifts are significant. We're talking kilometers of drift.
Agreed.
So if we go to this picture,
this one,
let's go to the white one. Yeah. So this drift, there's the little payload, this gray box. So it's in the picture. Yeah, the gray box there. It's off vertical from the vertical dashed line by kilometers of distance. So that means this cable is getting bent.
It's getting like whipped to
vertical.
the side, like way to the side.
Yeah. If you don't compensate for that, it would be really bad.
I guess do you compensate by having your orbital, like wherever your platform is, it needs to be powered so that you're adding 11 meters per second to the east. So that way your cable ends up being straight. But then it's a constantly powered platform.
Right.
Like
you
want to
avoid
losing
that.
energy. Like
I don't know. So somehow you need to compensate. Maybe there's a clever way to compensate with like payloads going up and down in a continuous manner. So like the drift to the west is compensated by some other drift to another direction, and you do it in some clever way, keeping track. You'll be fine. Maybe.
Or you could have, instead of having if here's Earth and your cable, instead of having a platform, you have a ring around the whole Earth, and that cable is just allowed to slide around the ring. And then when you
Okay.
want to disembark your payload, you just gotta make a little leap. You gotta make a leap of 11 meters per second.
Someday,
No chance. Just absolutely.
when we have
just
space
splattered.
elevators.
Just no chance to do that. 11 meters per second. Okay.
Yeah.
11 meters per second into miles per hour. 24 miles per hour. Yeah, you can't jump like that.
No.
Don't do
Okay, so for this calculation, I think what I need to do is make those calculations on Desmos clearer.
Pardon?
It's a mess right now. And I think I also need to do the continuous calculation. I think that's the next step.
Set it up as an integral and evaluate it.
Yeah. And then see if I can find some literature on like drift compensation. That'd be pretty cool because I'm sure it's out there.
Yeah. If not, that's somebody's PhD project.
Yeah. This picture's cool. This is like giving a scale for what a space elevator at the equator would need on Earth. And the cable needs to be 20,000, I think it's 20,000 kilometers long. So the engineering challenges are significant. So like things in orbit are super close to the Earth. And if you go to the end of the green line, that's how long the cable needs to be. It's
To get to high Earth orbit?
This gets to geosynchronous orbit.
Oh, to get to
Oh, it's 35,000.
36 kilometers,
36.
1,000 kilometers.
It's just a cable that long holding itself together under tension. It's just significant engineering challenges.
That'd be cool, though. What a feat of humanity. That's some full-on sci-fi. Like, oh, these people are smart.
Yeah.
Okay, but is that because we don't have it now? If we were to look back, like if we were future humans, like, oh yeah, you just have a cable, like whatever.
It's just cable. Just drop cable down, bro. Like
maybe the thing you didn't think about was starting from the top and going down. Like, okay.
Okay. Yeah.
Cool.
Yeah. Cool. All right.
Next time.
I think that's it. Yeah. Next time.